Yeah, so here we are. So welcome here. This is a hydroelephone. It's an underwater musical instrument, underwater pipe organ, and this is our lab here. You see some of the other underwater musical instruments over there as well, and some of the early ones. The first ones we built, you had to be underwater to hear them. You had to actually, we had all the audience members underwater in a little sort of fun little performance, and we were also underwater, but over time we got them so that they could be heard or audible above the water. Each jet is an individual pipe, so when I obstruct this jet, so it's a musical scale, and you play it by just obstructing the jet, so you block it a little bit. There's a little bit of water flows through the whistle. There's a separate underwater whistle associated with each jet. And we also have a listening device called a hydrophone in each jet, so that we can actually hook it up to a computer and have the computer listen to the vibrating sounds in the water and use it to control things. So you can control sound and lighting and everything by this control surface if you want. And so it's when you obstruct the jet, there's a little T-fitting and it comes out of the jet, and when you block it, it pushes the water through the underwater whistle into a separate chamber for each jet, so that each jet has its own sounding. And so, for example, if I obstruct 3 jets at the same time, A, C, and E, there's D minor, and C major, and I obstruct these 3 jets. Now I can play harmelodically, harmelody, an intertwining of harmony and melody. So we can obstruct this jet. And I can gradually shift the emphasis. There's a C major with the emphasis on C, emphasis on G now, F major with the emphasis on A, C major with the emphasis on G, and now F major with the emphasis on F, C major with the emphasis on E, and G major with the emphasis on B, and then C major with the emphasis on C. And I call that harmelody, the intertwining of harmony and melody. So we have this kind of, if I play that in A minor, it's a gloomy day today. try that in B minor. So now that's called a hydroelephone, underwater pipe organ. So this is kind of an invention back from the 1960s. In my childhood, my kindergarten teacher said to me, there's three kinds of instruments: strings, percussion, and wind. And the strings make sound from vibrations in solid matter of one dimension, and percussion is solid matter of two-dimension or three-dimensional bulk solid, and wind is gas. So when you say strings, percussion, wind, what that means is solid, solid, gas, the three states of matter. And one-dimensional solids, multi-dimensional solids, and gases. And I thought that was a really strange taxonomy. I was really bothered by that strings, percussion, wind taxonomy, so I said, couldn't you have a musical instrument that makes sound from vibrations in liquid? And of course everybody told me, well, liquids are not compressible, that's impossible. And I said, well, if liquids are not compressible, then the speed of sound in liquid would be infinite, and we could communicate across the ocean in 0 time. So we know actually that liquids are compressible, it's just the acoustic impedance is different. So we experiment a lot with underwater things, vibrations in underwater, to make things that would work underwater. And some of these early Hydroelephone examples over there, some of those early instruments are examples of early attempts at making hydrolephones. There's some more on the wall there, there's some other instruments on the wall. And so these are early attempts. And out in front of the building I've also got a hydroelephone there. Out in front of the building. And so the idea here is that it's a human-machine interface that's based on water. And so water is this medium of human-machine expression. And Ontario has the world's largest lake, Lake Superior. And the Great Lakes in Ontario hold 21% of the world's fresh water, 85% of North America's fresh water. So in many ways, Ontario is water capital of the world. And so growing up in Ontario, one of the things that I came up with in my childhood was called wearable computing. I attached all these computer systems to my body, these eyeglasses, these smart eyeglasses, these all this. But we'll just jam, we'll play and have some fun. How about like House of the Rising Sun maybe or something like that?
Improvising around that island.
Yeah. What else could it, like, Puff the Magic Dragon?
Nice. I'll give you some rhythm and then just jam. Go crazy like.
Yeah,
Good.
Good. Okay, so this is the Hydroelephone, the underwater pipe organ. This is an instrument that we invented back in the 1960s, and it's kind of perhaps the first sort of human-machine water interface, maybe. And so the idea of the Hydroelephone is to interact expressively and engage with the machine. And the Hydroelephone has these water jets, and you obstruct the water jet. That's and so, for example, each jet has a separate underwater whistle in it, and so when I block that jet just a little bit, there's a flow channel, and the water goes more easily out this finger hole than it does go through the underwater whistle. And in fact, it draws a negative pressure due to the Bernoulli effect on the underwater whistle, so when I obstruct it, it pushes it through the whistle, and it gradually increases the flow. And so if I play multiple jets, we get a chord like A, C, and E is A minor, C, E, and G is C major. And you can play harmologically, so I can take C, a little bit of E and G, so I can play very little bit, so I can gradually and fluidly transition from the C major with emphasis on the C to a C major with emphasis on the G. harmony and melody. And so you take a simple song like Twinkle Twinkle Little Star or something, very simple children's song, and suddenly give
Steve,
it...
they can't really hear you. Maybe turn the water off a little bit, or speak louder.
Yeah, or give it expression. You know, we can make it expressive. Expressivity is possible. We can get this level of expression that's not possible with other instruments. It's very fluid and flowing. And so the idea here is that we're able to use this as an expressive tool. And water is very important. You know, the Ontario is home of Lake Superior, which is the world's largest freshwater lake. So, and the Great Lakes we have here hold 21% of the world's freshwater supply, 85% of North America's freshwater supply. So in some sense, Ontario is water capital of the world. It's, you know, water stewardship is really important. And so this idea of water-human-machine interaction is something born of the 1960s. Growing up, you know, we would play around with these different kinds of water interfaces and build things. So I've done a lot at the intersection of humans and technology. The wearable computer from my childhood was an exploration of attaching computer systems to the body. But then water is another element too, you know, water and electricity. I was always afraid to swim because I had all this equipment on my body and water and electricity don't mix and everything. So I never really learned to swim in my childhood because I had all this cyborg technology on me. And so that was always the frontier. And I had this dual world of cyborg technology and water. And so what we sort of had this water cyborg idea that water is a medium of expression and interaction. So we put all kinds of sensing in here to control things. So the Hydroelephone, an H2 organ, and all these different kinds of instruments were instruments of sensing and meta-sensing. So these are some early Hydroelophones. There's Dr. Eugene Draw on violin here, and these are some early Hydroelophones here. The original ones, you had to be underwater to hear them. The audience members and the player had to be underwater, but then we developed gradually a system whereby they could be heard above the water. And so each of these water jets is separately played, and we can get very expressive sound. We'll do, let's do that D Dorian. So yeah, this is the Hydroelephone, the underwater musical instrument. And so it was kind of a long journey into the exploration of water, humans, and technology. And it's a really important nexus, a really important intersection. We have the cyborg technology. You know, we're all cyborgs now in many sense, but you know, the idea of humans and machines intertwining or intersecting. We have all these human-machine interfaces now that bring us these sort of superhuman capabilities. And so these are some of the early prototypes. When I was growing up in the 60s, you know, we'd play around. I'd try and plot graphs and sound waves on the television screen, and then you know, my dad got me that cathode ray oscillograph there in my childhood, and it wasn't working properly, and the time base didn't work, and the dot only went up and down. So I kind of developed this. You know, I wanted to see it. I was impatient, so I put it on rollers like this so I could slide it back and forth on my workbench really quickly while I was looking at the screen. And then I was able to see. And what I discovered is I could see sound waves in air, in water, and in solid matter. And so I played around a little bit, you know, and we would often use radar to measure cars and boats and that sort of thing. So marine radar in the early days. My in our family, some of our relatives were in the Navy and on the East Coast, and so we'd often find ourselves touring ships and looking at radar and everything. And I started playing around with marine radar, and so I developed this interactive water-human-computer interface kind of thing that was called the Sequential Wave Imprinting Machine, SWIM. And what we do is we'd swim this hydrophone through the water and look at the response of it on a lock-in amplifier. A lock-in amplifier is this kind of instrument here, PAR124A, right here, is to this day the best amplifier ever made in human history, even like at Stanford University, Los Alamos Labs, MIT. They all use this amplifier when they're trying to measure the smallest, weakest signals. You know, and that's the gold standard. Nobody to this day has ever built an amplifier better than a PAR124A. And so that's kind of what I grew up with, 1961. And I was born in 1962. So, you know, it's from my childhood. This is what we use, and it's still to this day the best amplifier. And this is what we did, is we'd put a hydrophone on there and swim it through the water and put it on the oscilloscope with a broken time base and move the oscilloscope back and forth together with the hydrophone like this. And that would allow us to see the sound waves in the water. So it was perhaps the world's first water-human-computer interface from many, many years ago, called the Sequential Wave Imprinting Machine. And we did develop many other things. The Hydroelephone is another interface. And the word interface is a double entendre. It means the boundary between different media like air and water, for example, the air-water interface. And it also means the computer interface, the border. So the border between humans and computers is the computer interface. The border between humans and water is the water interface. And there's also a border between water and technology, which is another interface. So you got these three interfaces. And so what we mean by water human computer interface is this interplay between these three borders and how they intersect. We can think of it as three circles on the Venn diagram. I use planet Earth is blue because it's mostly water, so I use that as the water circle. And then you've got the human circle. You know, you think of the Vitruvian person, you know, standing in the circle. That's kind of the iconic symbol of humanity, is a circle also. And then we've got the computer screen, which in the 1960s, these were all these round, green, glowing screens with analog computers. Typically, back in the day, computers were analog, and they had round screens with the green glow that would vary. And we have this Pascal Fourier synthesizer here, or other things like that that do Fourier synthesis on waves, and see these waveforms and compute stuff analog. And so when I think of water-human computer interface, I'm thinking of things like we built back in my childhood, which was these things that had this cathode ray screen, you know, the green glow of the tube. I'm going to say I've got one right here. This is your typical cathode ray tube. It's got an electron beam here. It shoots electrons at the screen, and there's a phosphor on the screen that glows. And we'd move that tube back and forth like this together with a hydrophone. So this tube would be on a vessel, like a little raft or something, and it would slide along in the water, and there'd be hydrophone in the water. And as we moved it along, we'd be exploring interactively and computing this interplay. So we had these really funny boundaries that didn't belong. So you got this tube running at, that one there runs at 2,600 volts. This one here only runs at 1,300 volts, but it's still a fairly high voltage. And so you got this high voltage thing next to the water. You got this interface between technology and the water, and then you got this other interface between the human and the technology, and between the water and the technology. So you get these three intersecting circles, and how do they interplay? And it's really interesting what that means. And then in 1998, we took this to University of Toronto, and in a collaboration with the McLuhan program, Marshall McLuhan, famous in the area of culture and technology. So the McLuhan program and Department of Electrical Engineering, we held a series of deconferences, which are kind of inverse conferences. And the idea of the deconferences was to explore the interplay between water, humans, and technology. And we did this. We created a whole bunch of different inventions, like an interactive shower system for mass decontamination, and all kinds of smart technologies using water and human computer interfaces. And so we held our 1999 was Decon 0, the first one, and then we had Decon 1 was in 2000, and then Deconference 2001 we turned into an art exhibit at Gallery TPW. Deconference 2002 was held right here in this building, and this building is called Decon sort of informally because I live here with my wife and 2 children upstairs, and downstairs is just my crazy lab, you know, where we can build stuff. And I've got milling machines and TIG welder and lathe and, you know, all that kind of stuff. You have to make things, and we would build stuff here and just have fun. We founded Interaxon out of here, the brain sensing company that makes a product called the Muse. My students and I and Ariel Garten founded that company right here in this space, and it kind of grew. We founded quite a few companies out of my home here, and so this has been a wearables center, and it's also the center kind of water, humans, and technology we call Decon. And so, Dr. Thank you very much for Dr. Eugene Draw for this beautiful musical fun.
Thanks, Steve. Thanks for having me. Always a pleasure.
And a big round of applause for Dr. Draw here. He's played with us at the Beaches Jazz Festival, and we've had this fun long history of hydroelephone music and improvisation. So I want to get started with Robert's talk. So Robert should be on. Is he on now? Okay, liquid nitrogen. BCs, B's and F's only.
Nice. Each one holds up 11.
Yeah, it's kind of sort of dissonant, sort of
Yeah.
accelerating the dissonance and consonance. And yeah, let's try.
Nice. Nice.
He's not answering, so maybe you want to play till the break?
Yeah, so we'll
Or we
go
could talk.
till, how long do we got?
10:41.
Okay, cool.
Oh, then it's just not cool.
Also,
Jam it out.
Lee Opperman is ready to present. So
Oh,
we could do that
actually, why
now.
don't we just have him present now? Yeah, that's a great idea.
Maybe turn that off and we'll switch the audio.
Yeah, that's a good idea.